So we did all this naming stuff on Thursday. We did a bunch of practice. There's going to be more practice tomorrow in lab. We've got all these great examples of actual compounds for you to look at and describe as well as name. So that should be interesting. We're also going to talk a little bit more about mass spectrometry tomorrow. I get to actually use a mass spectrometer and do some measurements with that. So today we're going to finish up, or I don't know if we'll actually get through the whole thing, but continue on with chapter 3. We talked about the composition of compounds in terms of like what elements there are. That was the naming thing. So now we want to extend our idea of molar mass, which we looked at the periodic table back in the last chapter and talked about those red numbers as the average atomic mass. Extend that to compounds and then talk a little bit about what kinds of things we can now do when we can convert between counting atoms and weighing them or knowing their masses. All right. So the first part is pretty simple, and you've probably done this before. Formula mass or molar mass for compounds. So like we know that the average atomic mass for carbon is 12.011, and we know that that's AMUs, atomic mass units for one atom, or that same number is the amount of grams in 1 mole. So that same number can mean two different things. We can use it for two different calculations. That's where the whole idea of the mole comes from. What if we extend that idea to a compound? How do we calculate a formula mass of CO2? Yeah, go ahead. Yeah, you just add all the masses together. So we know that carbon dioxide is made up of one carbon atom and two oxygen atoms. So we can say, we'll take our 12.011 for carbon, and we'll add it to 2 of oxygen, which to a couple significant figures, we'll say 16.00. Right. So we add up 1 carbon, 2 oxygens, and we've got the mass of carbon dioxide. We can also use that as a molar mass. That same number tells us how many grams are in 1 mole of carbon dioxide. This is going to be extremely useful because in chemical reactions, we need to count things, but in actual reality, we can't count them because they're too small. So we weigh things, we use this as a conversion factor, and that way we can determine the number of things that we have. So if we wanted to know something like how many moles are in (63.5 grams of CO2. We do that just like any other conversion problem. We would say 63.5 grams of CO2, and we're going to convert grams to moles. And the conversion factor that we use for that is that molar mass that we calculated, 44.01 grams per mole. So 63.5 divided by 44.01 gives us 1.44 moles. All right, so we can do that, right? We could also then, if we wanted to, go from moles to molecules using what kind of a factor? Yeah, Avogadro's number is 6.02 times 10 to the 23rd, if we wanted to actually know how many pieces are in there. All right, let's extend this one more. How many moles of each type of atom, so we've got C and O and CO2, how many moles of each type of atom are there here? How do we figure that out? If we've got 1.44 moles of carbon dioxide, how many moles of carbon atoms do we have? Can you tell from the formula? Remember that a mole is a count. Yeah? Well, not quite. You're right that we have to find the moles of C, but we don't actually have to subtract it because we're just asking how much is actually there. If we look at this molecule CO2, what is that made out of? Each CO2 molecule is 1C and 2O, right? 1C and 2O. So if we had, let's forget moles. I think we're getting confused by moles here. If we forget moles and we just think about counts, if you have one carbon dioxide molecule, how many carbon atoms do you have? One. If you have 100 carbon dioxide molecules, how many carbon atoms do you have? 100. If you have a dozen carbon dioxide molecules, how many carbon atoms do you have? 12, also a dozen, right? So if you have a mole of carbon dioxide, how many carbon atoms do you have? Or how many moles of carbon atoms do you have? Sorry. If you have a mole of carbon dioxide, how many moles of carbon atoms are there? There's one, right? Because every molecule of carbon dioxide has one carbon atom. So if you have a mole of them, just think of it as a big batch, you have that same number of moles of carbon atoms. So one way we can figure this out is to think about using that ratio as a conversion factor. So since each carbon dioxide has one carbon and two O's, we can write things like this, that there is 1 mole of carbon per 1 mole of CO2. There's 2 moles of oxygen for every mole of CO2. You see where those factors come from? It comes right from the formula, right from the subscripts. So to answer this question, we have to do 2 calculations. We can take that 1.44 moles of CO2 and multiply it by a factor that cancels the moles of CO2 and instead gives us the moles of whatever atom. Those are those factors we just wrote. So there's 1 mole of C per mole of CO2. So that means that we should also have 1.44 moles of just C. Similarly, with oxygen, we can do the same thing. We just have 2 to 1 instead of 1 to 1. So there are 1.44 moles of carbon in 1.44 moles of CO2, and 2.88 moles of oxygen. This idea kind of messes with people sometimes because it seems strange that you actually have, it seems like we're saying that we have more oxygen than we have CO2. Right? It seems like if we have 1.44 moles of CO2, that part of that should be carbon and part of that should be oxygen. But that's not right because we're not talking about the mass. We're just talking about counting it. So if you've got a thing that has two of the same kind of piece for every unit, and you've got so many units of them, you've got double the number of that piece that you need to put that together. So when we're talking about counting things, we're talking about counting atoms. You're going to have more of the individual pieces than you have of the whole. Any questions about that idea? All right, so we're going to put these things together with one more thing, which is the composition of compounds, and then we'll actually be able to determine molecular formulas or empirical formulas from experimental data. So the other way we want to look at this is the composition of the compound. How much of the compound, mass-wise, is one atom versus another one? We could talk about mass percent, we could talk about mole percent. So if we want to know, for instance, what percent by mass of CCl2F2, this chlorofluorocarbon, or CFC, is chlorine. So how much of the mass of that compound, what percent of the mass of that compound is chlorine? Any idea how you would do that? So let's start with the denominator. All right, if we're making a mass percent, what are we going to use as the total mass of that compound? Say it louder. Yeah, the molar mass. So we're going to calculate the mass of 1 mole of that whole compound, and that's going to be our denominator. So if we just kind of think about what we're going to be doing here, to make a percentage, we're going to take the mass of Cl over the molar mass of the entire compound. So that's going to look like this. The molar mass is, let's do that kind of separately over here. So we've got 12.01 plus 2 times 35.45 plus 2 times, is that 18? 18.99. I'm getting too old, I gotta use my periodic table here. Okay. Yeah. All right, so let's calculate that. Actually, I've got it here. It's 120.91. So that's our total mass. All right, so then what are we going to put on top? How do we find the mass of just the chlorine in the compound? So do we put 35.45 on top? Have to multiply by 2, right? Because there's 2 chlorine atoms per compound, per formula unit. So we have to go, we have to talk about the total amount of chlorine in the compound, which is going to be 2 times that mass of chlorine. All right, so if we calculate that out, we're going to get 0.5864, which is 58.64%. So this compound is 58.64% chlorine by mass. All right, and we could do that for all the other elements as well. So let's say we do it again for carbon. We find out how much carbon is in there. Would we have to do the same calculation for fluorine also? We could, but we could take a shortcut. We could just subtract from 100%, right? Because everything has to add up to 100%. So that would be the other way to do that. All right. So one way we can use this now, we're not going to necessarily just calculate mass percent just for fun. We want to use that. We want to know why do we need to know the mass percent in a compound? And the main reason is to kind of use it as a conversion factor. So take a problem like this. Oops, this is from the book here. The FDA recommends that you consume less than 2.4 grams of sodium per day. That's 2,400 milligrams. It's our recommended daily allowance of sodium for an adult who hasn't been otherwise directed. How much actual salt, table salt, NaCl, can you consume without exceeding this recommendation? So the recommendation is for sodium ions, Na+. But if you were to just if you were to measure your food and stuff, if it was already prepared food, you'd look at the nutrition labels. But let's say you're making everything from scratch. You want to know how much actual salt can you add and be within those guidelines. Well, salt isn't just sodium, it's sodium chloride. So how do we do that? Well, the easiest way to do this, and there's a bunch of these types of questions in your homework if you've been working on that, some more difficult than others, is to think of a percentage as a conversion factor and then set up your unit conversion just like you did in the previous, or in chapter 1, which is what we've been doing all along. So we can think about this as a conversion factor once we know the mass percent of sodium in sodium chloride. So first we're going to find the mass percent of sodium in sodium chloride. So that would be 22.99 grams per mole sodium in I thought it was here, but I'll have to just calculate it. In the total sodium chloride, which is 22.99 plus 35.45, so 58.44. .99 divided by 58.44 is 0.3934. So that's 39.34% sodium in sodium chloride. All right. So let's think about that word percent. What does that mean? What is a percent? Measure out of 100, exactly. So another way of saying 35 or 39.34% is to say that there are 39.34 grams of sodium in every 100 grams of NaCl. So if you know the mass percent, you can just put it over 100 grams of the compound, even if you don't know what the molar mass of the compound is. let's say it's some mixture of something that you don't have a molar mass for, then you can still use 100 as your denominator because you got the same thing there. So now we can set this up as a standard conversion. 2.4 grams of sodium. And then we want a factor that tells us not how many grams of sodium. Let's cancel grams of sodium and instead have grams of sodium chloride. And that's exactly the conversion factor we just came up with using the mass percent. It's just we got to flip it. So that's 39.34 grams of sodium per 100 grams of sodium chloride. Right? And so that tells us that we can get about 6.1 grams of sodium chloride and still be, and that would be the limit of our sodium intake, so less than 6.1 grams of sodium chloride. So there are several questions in the homework. Did anybody do that? Like there's one about lead that's like fairly complicated that has multiple steps of this. If you think about it this way, you can actually still do that fairly simply in just one long stretch of conversion factors where everything is over 100. Anytime you're given a percent, you just take that number and put it over 100. And as long as you follow the units, so grams of this per 100 grams of this, and you're canceling your units appropriately, you should get everything in the right spot. Okay. So let's practice that first before we move on to the next topic. So here's a couple questions to try on your own or in groups. First, how many bromine atoms are in 35.2 grams of CH2Br2? CH2Br2, dibromomethane. Sorry, that's one compound. I kind of wrote it weird. Okay, so give that one a try. If you get that one, here's another one. How much silver chloride is needed to produce 155 milligrams of pure silver? they look like? If you're not, talk about how to do it. All right, did you get a chance to find these? Try these? So there's lots of ways to do the first one because, the order of operations, multiplication you can do in whatever order you want. For me, the most logical is just to find the number of moles and then go from there. Because whenever I see a mass of a compound and I'm asked to count something about that compound, it makes most sense to me to find the moles. If you didn't do that, if you like you could also do it like by mass percent and then convert that to moles of bromine directly that way. That's also fine. You should get the same answer, but so what I would do is I would convert 35.2 grams of the compound to moles. And to do that, of course, we need the molar mass. So we're going to calculate 12.01 plus 2.02, that's 2 hydrogens, plus 2 bromines, $173.83, is that what you got for the molar mass of that one? Okay, or 170. Yeah, we'll do that. 173.8 grams per mole. So 35.2 divided by 173.8 is 0.203, and that's moles of the compound. So now from moles of the compound, we just need to use the ratio of atoms, the moles of bromine per compound, and then get the atoms by multiplying by the 6.02 times 10 to the 23rd. So we could actually do this all in one step, but break it up just for clarity. So we take our 0.203 moles of the compound, and then we're going to convert from moles of the compound, CH2Br2, to moles of just bromine. And then to get atoms of bromine, we want a factor that goes from moles of bromine to atoms. Again, I always put the units in first just to make sure that everything's on the right side of the equation before putting the numbers in. That tends to help stop me from making mistakes in terms of putting the wrong thing on the wrong side of the fraction. So this one I know is that number. And then this one is just 2 moles of bromine per mole of compound, because the subscript of bromine in the compound is a 2. All right, so I'll take my 0.203 times 2 times 6.02 times 10 to the 23rd, which gives us 2.44 times 10 to the 23rd bromine atoms. All right, did you get something close? Okay, great. All right, number 2, how much silver chloride is needed to produce 155 milligrams of pure silver? So in this case, we have a compound silver chloride. So I added a little extra skill in here because you have to come up with a formula for silver chloride first before you can find the mass percent of silver in silver chloride. So what's the formula of silver chloride? Yeah, it's AgCl. Silver is one of those weird ones where yes, it's in the middle, but it only ever has one charge. So we don't use the parentheses. Silver is always +1. So if silver is +1, chloride is -1. Silver chloride, we know, is AgCl. Okay. Once we know that, then we can get the mass percent of silver in silver chloride. So that's going to be the mass of silver, 107.9, in silver chloride, which is 107.9 plus 35.45. That's actually grams per mole, sorry. Let's fix that. 107.9 divided by 143.35 gives us 75.3%. So silver chloride is 75.3% silver by mass. So then if we want 155 milligrams of silver, we want to know how much silver chloride do we need for that. Our percentage gives us that there are 75.3 milligrams of silver per 100 milligrams of silver chloride. Notice that I'm just staying in milligrams here instead of grams because the question doesn't specify what unit to put it in, so we might as well save ourselves a conversion and just keep it. As long as the units are constant, a percent is a percent. So percent, milligrams in 100 milligrams, grams in 100 grams, pounds in 100 pounds, all of that is still percent as long as the units are the same. So 155 times 100 divided by 75.3 is 205.8, or we'll say 206 since we've got three significant figures. So we need 206 milligrams of silver chloride to give 155 milligrams of silver. When you do problems like this, also always take a second at the end to stop and make sure that the answer makes sense. You know kind of what percents are at this point in your life probably. So if it's 75%, right, that's like 3/4. So if you get that you need 206 milligrams silver chloride to produce 155 milligrams, does that about make sense? Is that about is 155 about 3/4 of 206? Yeah, right, it's close. If we had flipped one of those fractions around, one of those conversion factors around, we would have gotten something that really didn't make any sense. Like let's say we flipped that percent by mass factor and we wrote 75.3 over 100. So then we would have gotten 155 times 75.3 divided by 100. We would have gotten 116. Now 116 is actually less than 155. So if we're thinking about that, that makes no sense at all. If you have a compound that has other stuff in it, and you want to take just the silver, you don't start with less of the compound to get more of the silver. That doesn't make any sense. So if you're like in the stress of a quiz or an exam, sometimes it's easy to just like punch the number out in your calculator and then just write it down and go on. Especially if it's a multiple choice question and 117 happens to be one of the choices, it's really easy to just pick that one and go on because you think you got it. So I always take a second and think, wait a second, does this answer actually make sense? Could this actually be the amount that I'm looking for or not? All right, question.
Yeah, so when it's asking for like the number of atoms in a compound,
Mm-hmm.
could you always just like find the total molar mass of the compound and use that like 2-to-1 ratio in this case to find the answer?
Yeah.
Whereas when it's asking for grams, you can find it based off the percentage.
I think that would be generally true. I would be careful about overgeneralizing that too much because it depends on what the question is asking. But yeah, I mean, if you're given a mass and you're asked about counting something, so atoms, molecules, moles, those are all counting type units, then yes, you're always going to have to convert through a molar mass. If there's a mass and it's also asking about a mass, in this case, because that's the only ones we've seen so far, it's going to be mass percent. As we'll see in the next chapter, that's not always going to be the case. Okay, so the next way to put this together, and one way that this is actually experimentally useful, is finding an empirical formula of a compound just from experimental data. So let's define a couple terms if you haven't heard them before. Empirical formula and molecular formula. Empirical formula is the formula with the smallest whole number ratio of elements. So what that means is, let's take the formulas. Let's take the empirical formula CH2O. Okay. Now that formula encompasses all of the simple sugars, carbohydrates. In fact, that's where that word carbohydrate comes from. Carbon and water, carbohydrate. That's the simplest ratio. It's telling you you have 1 carbon per 2 hydrogens per 2 oxygens. But in an actual entire molecule, you might have more than that. The molecular formula includes all atoms in the molecule. So for instance, glucose, the formula for glucose is C6H12O6, because a glucose molecule, if you actually draw it out, has 6 carbons, 12 hydrogens, and 6 oxygens. But the empirical formula is the reduced whole number ratio of that, which is CH2O. Lots of molecules can have the same empirical formula even if they have different molecular formulas. So you could have formaldehyde, which is also CH2O. You could have C2H4O2. You could have C3H6O3. You get the idea? Different multiples of the empirical formula. So the molecular formula will always be an integral multiple of the empirical formula. Experimentally, you can find the empirical formula. You can use a technique called elemental analysis to actually figure out the percents of each element in a compound. But the trick is, you can only figure this out by mass percent. So that when you actually feed the stuff into a machine, one of these elemental analysis machines, there's different types, you get back either mass of each element or mass percent of each element. So let's look at an example. I think it's easiest if we just work through an example. A compound is decomposed producing 24.5 grams of nitrogen and 70.0 grams of oxygen. And we want to find the formula of that compound. So what do you think we're going to do, since we have masses and we ultimately want numbers, we want formulas? How do we always get from masses to formulas? What? We convert using what? Yeah, we're going to use the molar mass numbers. So the first step here is to get away from the masses and into some actual numbers. So we're going to convert to moles first. Okay, that's the molar mass of nitrogen. 24.5 divided by 14 gives us 1.75. And then we do the same thing for oxygen. So we got 70.0 grams of oxygen. Molar mass of oxygen is 16, so 70 divided by 16 is 4.38. Okay, so at this point we actually do have a molecular formula. It's just not really, or we have an empirical formula, it's just not really the way that we usually write one. Sorry, my computer's extra angry about streaming today, I think. So the formula we can write now is N 1.75 O 4.38. So what do you think? Is that a good formula? I mean, it's not ideal, right? Because we know from the laws of multiple proportions that these compounds have to be small whole number ratios. Because that's how atoms work. That's how atomic theory works. You can't have 0.75 of a nitrogen atom. So what do we do? What? Yeah, we can actually simplify this by dividing by the smaller number. So if we take whatever the smaller number is, and if it's a larger compound, it would be the smallest number. We can see if we can find an actual whole number ratio. So 1.75 divided by 1.75 is, of course, 1. 4.38 divided by 1.75 is 2.50. So that gets us a little bit closer. Now we have N1 O 2.50. But we still got a problem because it's 2.50 and we still want those whole numbers. So what else can we do? Yeah, at this point, then the last step is to multiply to get whole numbers. So if we take that whole formula and we multiply it by 2, we get N2O5, and now we have a nice empirical formula. So this is a really nice tool. This is something that's used all the time to figure out the identity of an unknown compound or something new. The drawback is that you can, of course, only get the empirical formula here because we don't know if it's N2O5 or if it's N4010 or whatever, and so on, N6O15, whatever the actual molecular formula might be. We need a measure of the molar mass for that. We can't get that directly from this. Okay, so why don't you try one? And this time I'm going to give it to you a little bit different and show you how to do that. All right, we're going to analyze some aspirin. And we found the following data. 60.00% carbon, 4.48% hydrogen, and 35.52% oxygen. And we want to find the empirical formula. So how do we deal with this if we've got percents instead of masses? Last time we started with some masses, we converted the masses to moles, and then went from there. What do we do if we have percents instead? Yeah, we can just assume, because it doesn't say how much of the original compound we have. So we can just assume an easy number like 100. If we had 100 grams of the starting compound, how much mass of carbon would we have? 60. So we could just directly write all those numbers as grams and proceed just as we did before. The only other difference about this one from the previous one is that now we have 3 elements instead of just 2. But other than that, the technique is the same. So give it a try, follow through the steps that we just did, now with these new numbers, and see if you can find the empirical formula for aspirin. come up with a formula? There you go. What'd you come up with? C9H8O4. Do we get something different? What do you get? You got the same thing? C9H10O5. That's pretty close. Anybody get something else? Alright, let's take a look at it and see. Here. All right, so we're going to just first convert those, or just rewrite them as grams, and then convert to moles. So 60.00 grams of carbon is 4.996 moles. I have these numbers, so I'm just going to skip the conversion step, but we know how to do that. 4.48 grams of hydrogen is 4.44 moles, and 35.52 grams of oxygen is 2.220 moles. All right, are we together so far? So we converted all the moles. We write down a formula. So C 4.996, H 4.44, O 2.220. And then we divide by the smallest number, which in this case is 2.220, to try to get a reduced formula. So 4.996 divided by 2.220 is 2.25. 4.44 divided by 2.220 is 2. And then, of course, the other one is 1. So that gives us a slightly reduced formula of C2.25 H2O, or O1. So we're close. So what do we have to multiply this entire formula by to get it to whole numbers? 4, right? Because 2.25 times 4 is a whole number. So we're going to multiply that whole thing by 4 and get C 9H8O4. All right, good. So there's sometimes a question of like, if you come up with a decimal like 2.25 or 2 point, point something, how do you know, first of all, what to multiply it by, but also when it's just an error? Because this is experimental data. Now this was an example, so I think they chose it to like be pretty much good. But in an actual experimental situation, you may not have a nice decimal like 2.25 show up. So what happens if you have something weird? In general, you're looking for, and again, you kind of have to go by the data, but in general, you can round, whoops, that's too many. You can round less than 0.1. All right, so if you came up with a number like 2.03 or something like that, you would call that 2. 2.09, you might call that 2. But you get 2.15, that's one. And something weird like that turns out, you may have to rerun the experiment or do some other stuff. But for our purposes, for what we're going to be doing, that should work okay. All right, so the last part of doing this, of empirical formulas from experimental data, is something called combustion analysis. in a combustion reaction, you have some sample which is usually made from carbon, hydrogen, and oxygen. But remember, we don't know how much, because that's the whole point of the analysis. And instead of actually doing a measurement like inductive coupled plasma or something like that, where you measure the direct percentages of the elements, sometimes the best you can do is just burn it and measure the byproducts of the burning. So you burn it in excess oxygen, and you end up with some amount of carbon dioxide and water, because those are always the products of combustion. And then you can actually measure how much carbon dioxide and how much water come off of the measurement, and then use that to back calculate your original formula. And that's called combustion analysis. So I'm going to show you an example of how that works. It's basically doing the same thing that we just did, but instead of knowing the mass of each individual element, you know these compounds, carbon dioxide and water. So you have to kind of work backwards from that and subtract out the oxygen. All right, so here's an example. Oops, that's the same example we did before. Example, combustion of a compound made of carbon and hydrogen. We'll not do the oxygen for now. Produces 1.83 grams of CO2 and 0.901 grams of H2O. Find the formula. So in this case, because it's combusting and producing carbon dioxide and water, instead of finding just the moles of carbon and the moles of hydrogen directly, we have to do it through the molar masses of carbon dioxide and water. So the steps are going to be similar. First, we're going to find moles. But we've got to do that for the whole compound instead of just carbon. So the molar mass of carbon dioxide is 44.01 grams per mole. And so that gives us 0.0416 moles. Now, using a scale that we learned earlier today, how many moles of just carbon is that? We've got 0.0416 moles of carbon dioxide. How many moles of just carbon? The same, right? Because it's 1 to 1. There's 1 mole of carbon per mole of carbon dioxide. All right, let's do the same thing with the water. All right, so how many moles of hydrogen are in that many moles of water? Yeah, it's double, right? Because there's 2 moles of hydrogen per mole of water. So we've got one more term here, because there's 2 moles of H for every 1 mole of H2O. So our actual amount of, whoops, I just meant to put carbon there. Our actual amount of just hydrogen is 0.100. C 0.0416, H 0.100. We can divide by the smaller number, 0.0416, and get C1 H 2.4. And then we're going to multiply that by 5 to get to whole numbers there, and that becomes C5 H12. So the actual empirical formula ends up being C5 H12. All right, so where this gets a little one step trickier is if you have a compound that also has oxygen. Because when we get moles of carbon dioxide in water, we can't just measure the moles of oxygen because that includes the oxygen that was added as part of the combustion. So if you're going to do that, you need to know the initial mass of the sample. Go through all this stuff, and then go back and subtract out the carbon and hydrogen from the original sample, and that gives you your mass of oxygen. Then you can go through and convert to moles. There's an example of that in the book, and there should be some practice as well. So with all of this stuff that we've done today, finding molar masses, finding mass percents, using mass percents as conversions, finding empirical formulas from experimental data, all this stuff, no matter how well you think you understand it at this moment, it will not go well for you on quizzes and exams if you don't take the time to practice it. So make sure that you're working through the homework, not just the online homework, but also supplemental stuff in the book. If there's a type of problem that you know is kind of getting you, you've got to do that over and over again 10 or 20 or 50 times until you're comfortable with that type of a problem. So try to set aside a couple hours each day to work on some of this stuff so you can get enough practice. The quiz on Chapter 3 will be on Tuesday, so a week from today we'll have a quiz on Chapter 3, and then that'll be, we're getting close to the first exam, which will be on this stuff as well. So tomorrow's lab, make sure that you have your report stuff from last week, from the density lab, ready to turn in, and then there's some pre-lab preparation for tomorrow's lab as well, getting ready for dealing with mass spectrometry. Any questions on any of that? If you bring your sheets, your nomenclature naming sheets from last Thursday, so that you don't have to redo all of that as part of the lab tomorrow as well. We only have a couple instruments that can do the mass spectrometry, so we kind of have to take turns tomorrow. So that's why there's this other part that you can be working on here while other groups are doing their measurement. It's a quick measurement, but we have to take turns. All right, sounds good. I will see you tomorrow morning.